So now we're going to talk about a new topic, and we're going to start with a definition. If the graph of f has a tangent line at the point CF of C, then this point is a point of inflection, or it's other times you might just call it an inflection point of the graph of f when the concavity of f changes from upward to downward, or downward to upward at the point. So it's a point where the concavity changes. So let's think about this in terms of a picture. I like to visualize these kinds of ideas. Let's take a function that looks like this. If you look over here, your graph is concave down. And then over here, your graph is concave up. So right here at this point on the origin, my graph switches from being concave down to concave up. And so this point right here, this is an inflection point. So we have the following theorem that'll help us find these inflection points. It says if C, f of C, is a point of inflection, or just an inflection point of the graph of f, then either the second derivative at C is 0, or the second derivative at C does not exist. So it won't always be the case that if your second derivative is 0, it doesn't guarantee that you have an inflection point, but it tells us where to look. So let's look at the following example. Determine the points of inflection and discuss the concavity of the function f of x, which will be x to the fourth minus 4x cubed. So, well, I've got to find my second derivative. Start by finding the first derivative, 4x cubed minus 12x squared. And then the second derivative be 12x squared minus 24x. Now, the second derivative always exists because it's a polynomial. So all I need to do is set it equal to 0. I can factor out a 12 and an x out of both terms. So I'm going to get two solutions. From this first part, I get x equals 0. From the second part, I get x equals 2. Now, these aren't guaranteed to be inflection points. I have to make my sign chart and verify, are these inflection points? So 0, 2. Pick your test points like we've been doing. So -1, 1, and 3. Plug them into your second derivative. And I'm going to go ahead and use the factored form. If I plug in -1, I'll get -12. It'll be a negative times a negative, which overall is positive. If I plug in 1, I'll get 12. 1 minus 2. It'll be a positive times a negative, so negative. And if I plug in 3, I'll get 36. 3 minus 1. Positive times positive, positive. So at 0, if I look over here at 0, my concavity switches from positive to negative. Or sorry, my second derivative switches from positive to negative. So my concavity changes. Same thing here. My concavity changes. So I do have 2 inflection points. Now you need to go back to your original function to get your points there. So if I go back, my function was x to the 4th minus 4x cubed. If you plug in 0, you get 0. If you plug in 2, you'll get 16. You'll get -16. So I get 2 points of inflection. And those points are going to be 0, 0, and 2, -16. I also needed to talk about the concavity here. So look back at your sign chart where it is positive, the concavity, it's concave up. Where it's negative, it's concave down. And now we just need to write that in interval notation. So it's going to be concave up from -infinity to 0 and 2 to infinity. It's going to be concave down from 0 to 2.